Hello, my name is Ludwig Eichinger. I'm an application engineer at Keysight Technology for simulation software. In this video, I will illustrate the workflow how to simulate electrostatic discharge circuits in PathWave Advanced Design System ADS from Keysight to protect the electronic on a PCB against damage. At each input and output interface, or say at each connector, the electronic should be protected with an electrostatic discharge circuit. In the first part of this video, I will show different methods how to model an ESD source or pulse. On the left side of this slide, there are three different methods how to model an ESD source. One method is to use a piecewise linear time source. Here in this source, I have just like a table. So we have start with the time, and then we have the first time point, and then the first voltage point, the second time point, second voltage point, and so on. The second method is to use the data access component, where I just assign a file with a table. Another method is also to use dataset source. Here I just assign the dataset file name and the expression. So this data can come, for example, from a scope. It is also very important to have accurate models for other components, such as for capacitors, ESD diodes, for the chip input impedance, and probably for the connector impedance and active devices and all other passive devices. Many vendors provide an ADS design kit or model library for their components. It is also possible to import SPICE models in different formats, such as PSPICE, SPICE 2G, SPICE 3, AT-SPICE, Spectre or HSPICE. In the second part, I will explain how to add the layout effects, run an electromagnetic co-simulation to get a deep insight to the design. Here we see the surface currents derived from the electromagnetic fields, which is excited by the ESD pulse. The dynamic current and voltages are displayed in a rectangular plot. It is really difficult to be allowed to present a real-life PCB example because most are confidential. This is the Advanced Design System. Left is the main window and right RF Pro. This design data is from SECO. SECO is a company in Italy. They allow us to use and show their PCB in a demo. This PCB is a COM Express module and can be mounted on any motherboard to have a quick access to high computing power. To build an example, I searched for a connector and found on the lower right side an SMA connector. So here at the connector, I will apply the ESD pulse. Here's a capacitor, here's the ESD diode, and here's the chip. The goal is to protect this chip and all other electronic from a high electronic discharge pulse. Before I go deeper into the layout, I will show how to model the ESD source. I open here the schematic. I have already prepared something. At the beginning of this video, I already talked about the piecewise linear source. This is available in the palette in the time domain sources and just drag and drop it down to the schematic and just define the time and the voltage in this line. The second method is to use a data access component to generate the ESD files. First, I wrote an MDF file. So the MDF file looks like this one. So I have here two columns, the time and the voltage. You just need to follow a few rules to be compliant with the syntax. So here in the second tab, we have here the independent variables. So we use here for the name, time, and also for the value. Then it ended up here. And it's also very important to use the type generalized multidimensional data. Now I will show how to assign this data to a component. So in this case, I just use here this voltage DC component. Place it here on the schematic, double click on it to get the dialog window. Here I switch over from standard to file-based. So here I can just choose the component, the data access component. So and here I need to put the dependent parameter name, which is here this voltage. So I just put it here, click OK, and then this source reads the data out from the data access component. Here I also built a voltage level controller in a sub-circuit. So I just used here an op-amp. When you type here, so we have different op-amps and define a gain, and this gain is here used, and then I just use a tuner and scale the voltage level. So I can also run a simulation like this one, and I get the voltage and the current. So, or if I want to tune, I just click on this little icon. Then I get here the tuner dialog window. I bring the data display in front. Here we can also store the first value. And now I just use the tuner, and then you see immediately the voltage level. In the next step, I will show how to add the layout model. So in the main window, I go to File, Import, Design. Here I choose ODB directory format. I navigate to the data, and then here you can also explore the layers which will be imported, the nets and so on. But we usually import everything, the complete design. Then I click OK, but make sure that you make a new library. During the import, you can also change the substrate, but it is not necessary yet. You can do it afterwards always in the substrate editor, and then click OK. So here in the ADS main window, we have three different views: the file view, folder view, and library view. In the file view, we can navigate to the complete database and open another workspace. So in the library view, I see which libraries are attached to this workspace. The library ESD_lib is the workspace library, which was generated when I generated the workspace. The CSA77 library comes from the ODB++ import. So this library uses the same technology what we have originally in the CAD system. Same layers, same units, and so on. And here we can find all cells which are included in this library. To have a better overview, I also can use the folder view because the ODB++ importer make here a nice structure. So it generates a components folder. So here in the components folder, I only have the cells for the package components. So the component cells only have a layout view. If we want to add a simulation model, then we also add a schematic view and put there the SPICE model. Later I will talk more about that. The ODB++ importer created here this folder with all subcells for the components, the top layout and the substrate. The other cells I added afterwards. Now I will open the top layout. So here in this layout I have a full editor available. I can change some line width and so on. I can go from layer to layer. For example, if I switch to layer 1, layer 2, 3, or I can expect with the navigators different nets. But this is actually not what I need to do now, because I only need an ear model, and therefore I just send this complete design to the RF Pro environment, and therefore I click here on this RF Pro icon. RF Pro generated a 3D structure for EM simulation. Here with these icons I can switch to the different view, so I can look from top, from bottom, or I can also look here, for example, from front and so on. But it's also possible just use here the rotating function. You can also use hotkeys like 7 to look from top. On the left upper area is the design tree. So we have here the nets, the components and substrate. And also if you have pins on the layout, it will be also displayed here. So the nets have different roles. Black is ground, red is power, and yellow is a signal. And in the middle is the analysis setup. So we can make here a right mouse click and choose full EM extraction. So that means all structure will be simulated. But this is impossible for this large structure. In this case, I only want to simulate a few lines, and therefore I use a new user-defined EM extraction and generate a new analysis. So at the beginning of my video, I already talked about here's this area what we want to simulate. So we have here the connector J2, the capacitor, the diode, and pin at the chip. So in the EM setup, I also need to assign simulation models. So lumped components such as capacitor, if I have a Murata, Samsung, or TDK, or S parameter, I can directly assign it here in this environment. But when I have a SPICE model, like for this D2024, I need assign this model into the cell. And therefore I go first to the layout. So we have here the D2024. To assign the simulation model, it is easier to start from the layout window. So this is the layout window. I go to the navigator. I search for the component D2024. And now I can click to this component. So it's here, you see, it's selected. And now I can push into the component. So this is a footprint of this diode. Actually, in the main window, here you see in this component, we only have a layout view. But now I will also generate a schematic view. And therefore, I just go to schematic in the layout window, generate update schematic. Now you see a schematic view was generated. I click OK. So what I did now, I synchronized the pins from layout to schematics that I have the same name and the same pin number. So next step is to add a component of the ESD diode. Therefore, I need also to attach the design kit to this workspace. So I found on the internet, was very quick, a design kit from Infineon for the TVS diodes. So you usually get a zip file. So you just click here, add zipped design kit, and then it automatically adds here to the favorite. You can also manage just over the library, but I prefer to do it over favorites. If I need it again, then I just activate or deactivate it in a quick way. So now the diodes are installed. So I just go here into the palette, Infineon TVS diode, and then so I just choose any one diode from this library and place it on the schematic. I don't use the same what Seiko is using. Actually, I don't know which diodes they have mounted on their PCB. This is just an example which should demonstrate the workflow. So before I connect the pins to the diode, I need to go to the layout to get the knowledge how the pins must be connected. So now I bring the ADS layout to front. So we see here we have the pin 1, 2 and 3. But it's better to go to the top hierarchy to get more insight how these pins are connected. So here I have also these little icons where I can view the numbers, the pin numbers or port numbers. So you see here, for example, this is pin 1, 2 and 3. That means the pin 3 is on the line. So this is my plus, and this 1 and 2 is minus. Then I go back to the schematic. I place the plus here on top. Minus is the 1 and 2. So next step, I need save it and generate a schematic symbol. Then I just go to Window here in this menu, Symbol, Create Symbol. OK, and then save it. Next step, I go back to the RF Pro environment. I close this first because I want to reload it to get the newest information from the SPICE model. Now I can restart RF Pro again. Either I double click here on this RF Pro icon or click here in the layout to RF Pro. So now I'm back in RF Pro. So I go straight to the component what I want to add to my analysis. Here, or first I make here an analysis, new user-defined analysis. So it's analysis 2, for example. Then I click here on this component. Then I just drag and drop this component into the model library. And you see it also automatically chooses the nets which are connected to this capacitor. And then I also want to have the D2024 in the component list. So here we see for the diode, there's no warning because it automatically picked up the simulation model and assigned it automatically. So we can also look to it. So we see this is a model from the cell view and also the symbol. So this is correct. And here for the capacitor, there's no model defined. And therefore we need to add now also a model for this capacitor. I just double click on add and choose model database. So here we can choose now from 3 different vendors, so either Murata, TDK or Samsung. You can also use here the filters in each section. So I search now for a 100 nanofarad capacitor. Type here 100 nanofarad, and now it offers me here different models. You can just click on one, and then you see also the impedance trace and also the data of this capacitor. So when I choose one of them, click OK, click Yes, and done. And the yellow warning has now disappeared.
The next step is to assign the input and the output port.
There are several ways how to generate ports. So here I can just click to the nets. You can also click on hide that you see what you have selected. Here in this case, you just make here a right mouse click, create ports or model groups. Then on the J1, I want to have a port, but here I don't want, I have already a component, so I just click do nothing. And the ground reference, here you can just choose ground RF, and then I click on OK. And now when I click here on this port, then you see we have here also a plus minus pin, so a port. Then the same I do now for the second trace, right mouse click and create ports. So here we have more than one. So this is it's a U277. I need a port, and for all other, I don't want anything connected because I have already connected my diode. Click OK. Now we have the two ports, the input port, output port, and also the nets. Now I have almost finished my setup, but before I start the simulation, I also need to define in options the frequency plan and other options. It is possible to have many frequency sweeps. Here we have different options: adaptive frequency sampling, logarithmic, linear, and single. So when I use adaptive frequency sampling, so this uses a very fast method to run a simulation. Here I have an example, it's a background, so you only need 0 Hz, 500 megahertz, 333, and 166, and then adaptive 100% of frequency range is covered. So with an adaptive sweep only and with the simulation option, so when I switch on momentum RF generation 2 and mesh domain optimization on, then the simulation runs in about 1 minute. This option is best when you only want to use this model for a transient simulation or for co-simulation or harmonic balance or any other simulation. And you don't have interest in the surface currents. When you want to visualize the surface currents on the structure, then you need to switch off the mesh domain optimization. Otherwise, you get here a warning. When you switch on in frequency plan, frequency storage. Make sure that you activate all frequency points of interest, because when you don't have this frequency in the simulation, then you will not see a near field at these frequency points. So first I only run an adaptive frequency sweep. Click on Done and double click on Run. In results, I can look to the S parameter, TDR, TDT, near field, far field, but only when I use momentum microwave or generate a test bench or generate a subcircuit. This is what I'm going to do. I double click here on Generate Subcircuit. In this subcircuit, RF Pro generated an EM co-simulation setup. It automatically connects the layout structure with the capacitor and with the diode. So this is a template what I generated at the beginning with the data access component to generate the ESD pulse. So now I need just to drag and drop the subcircuit from from the main window to the schematic window and connect it and run a simulation. So here we have the voltage and current at the input and at the output. So in the next step, I will apply at each node inside the subcircuit the voltage and the phase to apply to the EM field. We call it also circuit excitation. Now I load the near field in RF Pro. Just double click on near field. Here we have the excitation type. This currently is a single port, but now I choose circuit simulation dataset. So the dataset from the transient simulation. At each component pin, we apply the simulation result what we have from the transient simulator. So I here also need to change the frequency. And now I also change here some properties. Let's take 10 milliampere. So we see now here we have a higher current at the input, but to the chip it gets less. It's better if we switch off first all layers and switch on only layer 1, because this is the most interesting layer what we want to see. At the input pin of the chip, the current density is very low. At that higher frequency point, the adaptive frequency sweep only provides 4 frequency points. So the question is, what happens in the lower frequency range? Now I will go back to the data display to get more information. So here I can just insert a rectangular plot and plot the voltage at the capacitor input. This is near to the connector. So we see here the voltage versus time. Now I'm also interested in the spectrum. In ADS we have many functions. So now I'm looking for the function Fs. So the Fs function performs a time to frequency transformation. This is the function what I'm going to use. The Fs function generated the frequency spectrum at the input of the capacitor. This plot shows at low frequency we have a high voltage and higher current, of course, but at higher frequency we have a very small voltage. From the adaptive frequency sampling sweep, I only get a frequency point for 166 and 333 and 500 MHz. So in this range, but this is not of interest. So I need to add more frequency point in the lower frequency range. I add now at 10 Hz, 1 kHz and 10 kHz single frequency points and run the simulation again. I also did run a transient simulation with the new EM data. In RF Pro, the old data are still loaded, so I could unload it, but I can also leave it and load the new data from the new analysis. And I just make here a double click on near field. So here we have now 2 data available. I can show others or hide others. So now I see only the data of my current design. First, I deactivate all layers, activate the layer 1, which is of interest, choose a frequency, and also the new data set. We can also change here the scaling for that we see a little bit more. This is the current distribution at 10 Hz. So I can also switch to 1 kilohertz and also 10 kilohertz. So it seems that at 1 kilohertz we have quite a high current density. It is also possible to run an animation in the tab sequence to animate the phase from 0 to 360 degrees with 5-degree steps. Now I'm at the end and will conclude with a short summary. I illustrated the workflow how to simulate an ESD circuit in PathWave ADS. I presented different methods how to build an ESD pulse and a simulation template, which was used for a transient EM co-simulation. This simulation showed a low current density at the input of the chip. The goal was achieved. I hope you enjoyed the video. Thanks for watching.